Hello everyone, this video is for reviewing KTCE employment year of 2024. The KTCE stands for Korea Teacher Certification Exam. This is for both nowadays, both public and private, both um, public and private school. A few years ago, only um, only for the public high school or middle school, they require the score of KTC, and the private high school or middle school had their own style, own manufactured exam. It was different from private schools to school, but I guess 2 years ago, from 2 or 3 years ago, the both and public and private school became to have the same type of certification exam, which is made by KICE, which stands for Korea Institution Institution of Curriculum Evaluation. Curriculum Evaluation. Okay. Anyhow, on this video, I want to deal with the problem number 2, which is about statistics, specifically Poisson distribution. Math problem. Okay, let me give you a few points of this problem first. The first point of this problem is about unbiased estimator. Let me introduce two. The X bar for the population mean and sample variance for population variance. They are called the unbiased estimator for the mean and variance of population. It is because, by the way, let me briefly introduce their formula. X bar stands for when we have random sampling from population whose size is n, random sampling of size n, and then the sample mean, which is denoted by X bar. This is a sample mean. This is called a sample mean, and S square is called a sample variance. As you have already heard about it, capital X bar has a formula for it's a mean. It's sum of all the sample random variables, and it is divided by the size of the sample. And then the formula for the sample variance, capital S square, is is the square of xi minus its sample mean, deviation from the sample mean and its square, and we add them up, and then we divide it by n minus 1 here. The n minus 1 is crucial because it's not divided by 1 over n, divided by n. It is because when we have a sampling which satisfies that the sample mean should be same as the population mean, and then to do that we have to pay a price. The price for the sample mean being the population mean is that it reduces degree of freedom by 1. So actually we have size n of random sampling, but actually we can freely choose from x1, x2 till xn minus 1. It has a freedom, but for the last sample called x sub n, it should be no freedom for the nth sample, because it should satisfy this equation. Okay, so n minus 1 is a degree of freedom for the variable. Let me abbreviate degree of freedom by d dot f dot of x bar. Okay, and then the reason why they are called for unbiased estimator for each population mean and population variance is that it is because the expectation value for sample mean is the same as the population mean, and also expectation value for value of sample variance is the same as the population variance. This is why they are called unbiased here. Okay, so if you have already known these facts, and if you can use it, then life becomes more simpler. However, if you do not know, if you didn't know this unbiased estimator fact, there's always a way of handling this problem. Let me introduce it later. Okay, so let me directly dive into this problem. How can you use unbiased estimator to this condition? I can use sample variance if I divide the sum of square of variance from the sample mean. The inside of this parentheses here. If I divide this quantity by n minus 1, because the sample size is n here, and multiply n minus 1 outside, then we have the same thing. The value is 140. Okay, and then by the property of the unbiased estimator, this value is the same as the population variance. Okay, and for the case of Poisson distribution, population variance is lambda, and let me introduce for the in this case lambda is 5 because each sampling is randomly happened from the population which has a Poisson distribution which is lambda is 5. You need to solve the equation n minus 1 times 5 equals to 140 to find sample size small n here. And what if you don't use this unbiased estimator property? Then let's take a look at the second case. Here is the second point. Other topic than unbiased estimator. This is about Poisson distribution for independent random variables. Random variables, say capital X1, X2 through Xn, and they are all from the same Poisson distribution with parameter lambda here. And then let me define the new random variable here, which is sum of those all the random variable from capital X1 to capital Xn, and then this new random variable y also has Poisson distribution with parameter n times lambda here. This is the point here. I will cover this sketch of proof later. By the end of the video, the main logic is proof by induction, mathematical induction here. Use the induction to show that. And then for the second one, for the Poisson distribution, if of some random variable here, xi, follows Poisson distribution with parameter lambda, and then its mean and its variance are all the same as lambda. I will briefly show this one here, why this is so. First of all, you can calculate the mean of random variable x here, which is the same as for the discrete case. Poisson distribution is a discrete probability density, discrete random variable case. So the mean of this random variable x is x times its probability when the random variable takes a value small x, and we add them up, x from 0 to infinity. And then by a simple calculation, you will have e to the minus lambda and lambda to the x power here from 0 to infinity. And you will have, I can take out this e to the minus lambda term here, and then x over x factorial, x is cancelled out, so this will give us x minus 1 of its factorial here. And this lambda to the x, I can split it to lambda times lambda to the x minus 1 power, and its sum x from 1 to infinity, because when x is 0, this whole value becomes 0. Okay, 0 times its probability when the random variable takes value 0 is 0, so it does not contribute here. And by the way, this is nothing but the uniformly convergent function whose limit is e to the lambda here. So the result is here e to the minus lambda times e to the lambda, which is lambda, because e to the negative lambda is cancelled out by multiplication with e to the lambda. Okay, and to figure out its variance here, first you need to calculate mean for the random variable x times x minus 1. You can figure it out after I do the calculation here, why I choose x times x minus 1, not x squared here. It has a benefit, some benefit. So the new random variable capital X times x minus 1 equals to x small x times x minus 1, and I will add them up here from 0 to infinity. And by the same way, when either x equals 0 or 1, their multiplication is 0, so I can safely change its starting point from 0 to 2 here. Okay, and then let me I'm sorry, this probability should be is the when capital X random variable capital X times x minus 1 is the same as x times x minus 1, the probability as a probability is the same as when the random variable capital X equals to x. So by multiplying x times x minus 1 to its probability, e to the negative lambda times lambda to the x over x factorial here. By the same way, I can pull out this e to the negative lambda outside, and I can compute this term as x and x minus 1 term is cancelled out, so what's left is x minus 2 and its factorial, and I have e to the negative lambda outside. Its sum takes place from x is 2 to infinity, and I will separate the lambda to the x to lambda to the x minus 2 power and square of lambda here. Okay, I had pulled out, and its sum here, its sum x is from 2 to infinity. Its sum is also e to the lambda. If you compute this sky blue rectangle part here, and then what we had is e to the negative lambda times lambda square, which is lambda square. Okay, so from here, by linearity, I can figure out that this is nothing but mean value of x squared minus mean value of x, and I do know the mean value of x, which is lambda here. So from this property, I can figure out the mean of x squared is same as lambda squared plus lambda. Okay, so from the mean of x squared, and by using the relationship variance of random variable x is same as mean of x squared minus square of each mean, and then you will get this is lambda square plus lambda, and mean of capital X is lambda, so it's a square of lambda, and you will get just lambda here. So anyhow, for the Poisson distribution whose parameter lambda, its mean and variance are the same. Okay, obviously in this case, from the sampling, the lambda is 5. It has a specific value here, and let me manipulate this equation, the equation of mean of expectation value of sum of square of deviation from x bar and its sum, its expectation value. Let me rewrite this parenthesis by the intermediate value lambda plus lambda and minus lambda and plus lambda, and minus its x bar again. Here I can separate like those two parts here, and then I will square it, and then I do have the square of deviation from lambda over its square, and plus 2 times deviation from lambda, and the difference between lambda and its sample mean, and plus square of the difference between lambda and its sample mean here. Okay, and I will add them up, I will add them up here. Just sigma from I equals to 1 to n. What I have here is the last term is nothing but a constant, so this is n times square of the difference between lambda and sample mean x bar here. And then for the second term here, the index I only takes this first factor. Okay, so this is 2 times lambda minus x bar, and each sum is actually n times x bar minus n times lambda, and I can pull out this n to the front here, and I get 2n times lambda minus x bar and x bar minus lambda. So I can rewrite this one as, I can pull out the negative sign here, so negative 2n times lambda minus x bar and each square. Okay, so by the simplification of those last two terms, I have negative n times square of the difference between lambda and sample mean x bar here. Okay. Let me arrange this term as, so what I have is expectation value of sum of each deviation from the lambda, which is a population mean, minus n times expectation value of the difference square of the difference between lambda and x bar. Okay, so this is this term, and each term do have a meaning that this first expectation value is nothing but sum of variance of each random let me rewrite this one like this to be more clear here. So by linearity, I can pull out this sigma, and what I get is expectation value of the deviation from the mean, population mean, and each square. And I will take the sum from I equals 1 to n here. And then the second term is the same as minus n times expectation value. Here one caution is that the lambda is the same as the mean of the sample mean here. Okay, so because let me write this one. Instead of lambda, I will write the expectation value of sample mean x bar minus x bar, and each square and its expectation value. So here it is because expectation value of x bar is the same as expectation value of 1 over n times is sum of values of samples through from x1 through xn. This is not infinity. This should be n here. This is a finite average here. And by linearity, I can pull out those two vector 1 over n and sigma sign here, and take its expectation value. The population mean is lambda for the case of Poisson distribution with parameter lambda, and we have 1 over n times it's sum of constant term lambda n times, and lambda, which is lambda. So instead of lambda, I can substitute this term as expectation of x bar. Okay, so here's the meaning. The expectation value of square of each deviance is nothing but variance of each variable capital Xi, and I have summation. I goes from 1 to n, and for the second one, this is nothing but deviation from the mean with respect to variance of sample mean x bar, and its expectation value means variance of x bar. Variance of x bar here. Okay, that's the point. And the last punchline is that the variance for each random variable x capital Xi is constant lambda here. And then the variance of x bar, this is nothing but variance of 1 over n times capital Y. The capital Y was defined as a new random variable, which is sum of the sample variables from capital X1 through capital Xn here. So what we have is n times lambda minus n times 1 over n square and variance of capital Y. The n square comes from this constant vector when it goes outside. Since we square each deviance, 1 over n should be squared. So it has 1 over n square, and by the property of this one, which I will show you later by mathematical induction, the variance is new parameter n times lambda here. Okay, so with the calculation, we have the n square is cancelled out. We have n minus 1 times lambda. So this is the meaning of expectation value of sum of all square of the deviation from sample mean x bar in case of each random variable xi. Okay, so we reach it to the same conclusion here. Okay, for the last part, let me briefly show you the sketch of proof why the sum of n independent random variables, each of which has Poisson distribution parameter with parameter lambda, same parameter lambda is the Poisson distribution with parameter n times lambda. Here's the sketch of proof. I will use the induction here. So for the case of new random variable, say capital L is x1 plus x2, and each random variable has a Poisson distribution with parameter lambda here. Okay. I want to find probability density function for the new random variable capital L, which is the same as the sum of x1 and x2 equals to small l here. And since they are independent, so the case is independent and discrete random variable. So we have n plus l plus one case here, either 0l, 1l, 2l, and l0 here. We have L plus 1 cases here. So I have to add probability for each case 0 small l plus 1 small l minus 1 plus small l 0, x2 is 0. Okay, and since they are independent, with the independent case, the probability of two events A and B happen simultaneously is same as the multiplication of probability of event A happening and probability of event B happening here. So they are probability of x1 equals 0 times x2 equals small l, and this term is multiplication of x1 is 1 and x2 probability of x2 is small l minus 1 dot dot dot, and this is multiplication of two probability when the random variable is small l and when the random variable is 0 here. So this gives us a specific formula for this one. Since they all have the same parameter lambda here, what I have is e to the negative lambda times lambda to the 0 over 0 factorial times e to the negative lambda lambda to the l over l factorial. This is e to the negative lambda lambda to the 1 over 1 factorial e to the negative lambda times lambda to the L minus 1 power over L minus 1 each quantity factorial here. This is by symmetry, this is the same as e to the negative lambda to the L over L factorial times e to the negative lambda to the 0 over 0 factorial. Okay. There's some rules. It looks like they have some rules or common point. All the terms have same factor as e to the negative 2 lambda term, and their addition looks like lambda to the 0 lambda to the L over 0 factorial L factorial plus lambda to the L minus 1 factorial times lambda minus 1 factorial plus lambda to the L lambda to the 0 over L factorial times 0 factorial. Okay. And let me rewrite this term as to make you see the rule more conveniently. Let me pull out the L factorial term here, and then there's a mistake. This should be L, not lambda here. And then let me rewrite each term as like this by combinatories. L factorial over 0 factorial times L factorial and lambda to the 0 lambda to the L plus L factorial over 1 factorial L minus 1 factorial lambda to the 1 lambda to the L minus 1 plus L factorial over L factorial times 0 factorial lambda to the L times lambda to the 0. The L factorial on the nominator comes from this L factorial which lies on denominator. They are all cancelled out. Anyway, are you familiar with some of this term? This is nothing but a binomial term. Binomial expansion of lambda plus lambda, it's L power. This is nothing but this one because you know you have to take a look at the binomial distribution. If you are not familiar with this one, so let me arrange all the terms. Then we have e to the negative 2 lambda times 2 lambda and it's L power over L factorial. This is the probability of new random variable capital L equals to small l here. So what does it look like here? So this is nothing but Poisson distribution with parameter 2 times lambda here. Okay, and lambda goes from 0 to 1, 2, 3 to the infinity. Okay, so you can prove the case of the size n if you use the mathematical induction. By the property of binomial term here. So suppose that the new random variable for the case of k here, let me give you a sketch. This new random variable m has a Poisson distribution with parameter k times lambda here, and do the same thing. Show that new random variable capital M plus capital X k plus 1, you can call this one as t if you like. Show that the t has a Poisson distribution with parameter k plus 1 times lambda here. Please do it by yourself. You'll have fun. I don't want to take this fun from you. Okay. Anyhow, let me wrap up this problem. For this problem, the life gets easier if you knew the sample variance is unbiased estimator. So its expectation value is the same as the population variance, which is lambda in this case. And the sum of the variables inside the expectation calculation, the square of deviation from the sample mean, and for the case of sample variance, we have to divide it by n minus 1, which means degree of freedom of random variable x bar, and its expectation value is lambda. This is a simple logic for this problem, but if you didn't know that, then you can use this relationship, which says that the sum of n independent random variables, each of which has a Poisson distribution with parameter lambda, and their sum follows also has a Poisson distribution, but with a parameter n times lambda. That's the whole point. Okay, thank you.